friends, so far we have studied the analysis of the continuous beam by using the stiffness matrix method. Today we'll discuss about the analysis of the continuous beam by using the stiffness matrix method with the sinking and settlement of the support. Here the problem is analyze the continuous beam shown in figure by using the stiffness matrix method. The support C sinks by 9 mm. Take the value of EI, flexural rigidity, as 1000 kN meter square. Here at A, it is subjected to 20 kN point load. A to B, it is overhanged over a span of 1 meter. B is a roller support. B to C, that is 6 meter, which is subjected to a UDL of 20 kN per running meter. And in span CD, that is total length is 3 meter, and at a distance of 1 meter is subjected to a point load of 60 kN at a distance of 1 meter from C and 2 meter from D. D is the fixed support, C is the roller support, B to C is 6 meter. Here in this problem, here for different spans he has not mentioned any variation of the flexural rigidity, hence we have to assume that the flexural rigidity EI is constant throughout the length from A to D. First we have to find the settlement in each support, the effect of the settlement of C on different spans. Here there will be no change in the position of B. By observing this diagram, at C, the support C sinks by 9 mm. Here by observing that diagram, here in between B and C, with respect to horizontal position in portion BC, the rotation is clockwise. If you observe at support B or at support C, the rotation is clockwise, hence the settlement for the span BC is, that is positive, delta equals 9 mm for span BC, or convert that into millimeters, that is 0.009 meters, that is positive. Then by observing span C to D, here the rotation, relative rotation with respect to the horizontal, here the rotation is anti-clockwise. By observing the rotation either at D or at C, the rotation is anti-clockwise, hence the settlement delta equals, that is negative, that one equals minus 9 mm, or if you convert that into meters, that is minus 0.009 meters. Now A to D is overhanged. First we have to convert that overhanged portion, overhanged into moment, that is actual moment. Here the load is 20 kN and distance is 1 meter, and the moment about B is 20 into 1, that is anti-clockwise, hence that is minus 20 kN meter, which is acting at support B in anti-clockwise direction. Now find out the degree of freedom. The degree of freedom here at B, the degree of freedom is 1. It is free to, it allows the free rotation of the end of the beam at support B. Similarly at C, it allows the rotation of the end of the beam. Similarly at D, it is neither permitted to move nor permitted to rotate in any direction. Hence the degree of freedom is 2, that is theta B, slope at B, and theta C, that is slope at C. Now by considering theta B and theta C as the redundant, now The load due to the overhanged portion or pre-existing load. That is, we have considered B and C as the redundant. At coordinate 1 or at B, there is the overhanged portion, there is anticlockwise moment of minus 20, that is 20 kilonewton meter is already acting at that point. Hence, P1 is minus 20. At C, there is no such moments, hence P2 is 0. Then, the next step is to find the fixed end moment. We have already removed the portion BA, that is overhanged portion. Now, the fixed end moment due to the UDL acting on the fixed end moment at B due to UDL, that is minus WL square by 12, that is anticlockwise, minus 20 into 6 square divided by 12, that is minus 60 kilonewton meter. Similarly, from the other end, that is MFCB, that one is plus 60 kilonewton meter, that is clockwise. In span CD, that is MFCD is minus WAB square by L square. A is 1, B is 2, L is 3, then minus 60 into 1 into 2 square by 3 square, that is minus 26.67 kilonewton meter. Similarly, MFDC, from the other end, that is WA square B by L square, that one is 60 into 1 square into 2 divided by 3 square, that one is 13.33 kilonewton meter. Here, there is a settlement of the support due to the sinking and settlement of the support. The additional fixed end moments due to the sinking or rotation of the supports that we have to consider at coordinate 1 and 2. Then MF dash FBC, that is given by minus 6 EI delta by L square. Here A is constant throughout. Then by substituting the values for span BC, that is M dash FBC, that equals M dash FCB, that one is minus 6 into EI is 1000 kilonewton meter square, delta is plus 0.009 divided by L square, that is 6 square, that equals 1.5 kilonewton meter. Similarly, from the other end, that is MFCB is also minus 1.5 kilonewton meter. For the next span, the additional fixed end moment to settlement, that is M dash FCD equals M dash FDC equals, here delta is minus 0.009, then the fixed end moment is given by minus 6 EI delta by L square by substituting the values. Minus 6 into EI is 1000, delta is minus 0.009 divided by L square, that is 3 square. By simplification, here we will get 6 kilonewton meter. The net moment at point B, that is moment due to the UDL plus the additional moment due to sinking of the support, that one is due to the load, that is minus 60 due to the sinking of the support, that is minus 1.5. Therefore, the net moment is minus 61.5 kilonewton meter. Therefore, the load at coordinate 1, that is net load is P1L, that one is minus 61.5 kilonewton meter. Net moment at coordinate 2 or at point C, that is fixed end moment due to the point load, that is MFCB plus MFCB, M dash FCB, that is due to the sinking of the support. Then here in span CD, MFCD, plus m dash FCD due to the load and due to the sinking of the support. Since there are two spans are connected at joint C are at coordinate 2, therefore P2L equals MFCB is plus 60, M dash FCB is minus 1.5, MFCD is minus 26.67, M dash FCD is plus 6. By simplification here we will get P2L equals 37.83 kilonewton meter. Now we have got the vector due to the loads acting at coordinate 1 and 2 respectively. Now we can get the stiffness matrix by applying the unit rotation at coordinate 1 and coordinate 2 separately. Here now apply the unit rotation at coordinate 1 or at B by considering all the supports as fixed support. Then here at B, here theta b equals 1 due to the unit rotation at coordinate 1. Here the total length is 6 meter. It will undergo deformation like this as shown in figure. Then by using the slope deflection equation R for the near end, K11 equals 4EI by L, that is 4EI by 6, that is 2/3 of EI. K21 here at the far end, that is 2EI by L, that one is 2EI by 3, or that equals 1/3 of EI. Now we can apply the unit rotation at C, that is at coordinate 2. Due to that, both span BC and CD will get displaced as shown in figure. The deformation is as shown in figure. Now we can get the stiffness values in span, both the spans, that is for span CB, that is 4EI by L, for CD, that is 4EI by L, for span CB length is 6 meter, that is 4EI by L, for CD length is 3 meter, that is for near end, that is 4EI by 3. Then by simplification here you will get K22, that is the stiffness value at 2 due to the load applied at 2, the unit rotation applied at 2, that is 2EI. Then K12, that is stiffness value at 1 due to load applied at 2, that one is the in span BC, that is far end, that is K12 equals to EI by length is 6, that is 1/3 of EI. By observing the K values of K12 and K21, both are equal by the reciprocal theorem of Maxwell's reciprocal theorem of deflection. Then the stiffness matrix K is given by EI is constant, EI is common in all the elements, K11, K12, K21, K22. Here K11 equals 2 by 3, EI is common, K12 that is 1 by 3 EI, K21 that is 1 by 3 EI, K22 that is 2 times EI. Then EI we have removed outside, that is a common. Then the inverse of the stiffness matrix, that is given by here, first get the determinant value and then the transpose of the matrix. Here we know that the displacement vector is given by inverse of the stiffness matrix into the vector due to any loads already existing minus the load due to the moment at coordinate fixed end moment at coordinates 1 and 2, that is PL. Here the theta B and theta C we have considered as the redundants. Therefore by substituting the values K inverse equals 3 by 11 times EI, the elements of the matrix are 6, minus 1, minus 1, 2, and the load due to any the vector due to load, pre-existing load, that is minus 20 at point B due to the overhanged portion at coordinate 2, that is 0. Then at coordinate 1 the net moment is minus 61.5, and at coordinate C, coordinate 2 that is at C 37.883. After simplification we will get the values of theta B as 78.23 by A. Similarly, theta C equals minus 31.95 by A. By using these values of the unknowns, now we are able to find the final moments in the various spans, that is MBA. MBA is overhanged portion. We have converted that into the actual moment, but the resisting moment we want, that is 20 into 1, that is 20, that one is in clockwise direction. In clockwise direction as shown in figure in this diagram, that is 20 kilonewton meter, that is clockwise. Then MBC is given by MFBC plus M dash FBC. Since the support C sinks by 9 millimeter, hence we have to consider the fixed end moment due to both, that is due to load and due to the sinking of the support. Then plus 2 EI by L inside of the bracket 2 theta B plus theta C. That equals minus 60, that is due to UDL minus 60 due to the sinking of the support. That is, we have already calculated this M dash FBC by using minus 6 EI delta by L square. That one is minus 1.5. By substituting the values here, we will get minus 20 kilonewton meter. Here, not that, don't take delta as it was calculated as M dash FBC. Then MCB. MCB equals MFCB plus M dash FCB, that is due to sinking of the support, plus 2 EI by L inside of the bracket 2 theta B 2 theta C plus theta B, that is after simplification. MCB equals 63.28 kilonewton meter. MFCD plus M dash FCD plus 2 EI by L inside the bracket 2 theta C plus theta D, that is minus 63.28 kilonewton meter. Then MDC, MFDC plus M dash FDC plus 2 EI by 3 inside the bracket, that is theta C, theta D is 0, then that equals minus 1.97 kilonewton meter. Here, by observing the moments, this one is 20 kilonewton meter, that is clockwise. This one is 20 kilonewton meter, that is anti-clockwise. Then this one is the net moment, that is just now we have calculated 63.28. This is clockwise, and this one is anti-clockwise, that is MCD. MCD, that is minus 63.28, that is anti-clockwise. MDC, that is minus 1.97 kilonewton meter, that is anti-clockwise. Here, by observing this, these two moments are hogging moments, and these two are hogging moments, but this one is sagging moment. Here, if you want to draw the bending moment diagram, here at B, draw the ordinate of 20 kilonewton meter above the reference line or datum line, since that is hogging. Similarly, draw an ordinate of 63.28 kilonewton meter at C. Then at A, bending moment is 0. Join this by a straight line, since the bending moment variation is a straight line from A to B. That is, bending moment is given by y equals mx plus c, that is 20 into x. Here, that is negative. This one is negative bending moment diagram. Here, join these two ordinates by a straight line. Then here at D, the moment is sagging. Hence, we have shown below the reference line join these two ordinates by a straight line. This one is negative bending moment, this one is positive bending moment. And then the simply supported beam bending moment. Here in between B and C, it is subjected to UDL of 20 kilonewton meter. The maximum bending moment is WL square by 8 at the center, and at the support the bending moment is 0. By overlapping this, you will get the net bending moment as shown in figure by the shaded portion. This portion is positive, this remaining portion is at support, that is negative. Then similarly in this portion, the maximum bending moment occurs below the point load, that is 60 into 1 into 2. That one is 60 into 1 into 2 divided by 3. Total length, that is 40 kilonewton meter. Here we have to overlap this. At support it is 0. At both the support below the point load, that is maximum, here by overlapping the bending moment diagram. Now to draw the shear force diagram, now we have to calculate the support reactions by taking moments of all the forces about C. First we have to consider the RHS portion by closing these, and then here in the right side of C, here VD into VD into 3, that is anti-clockwise. Then 1.97, that is also anti-clockwise. 60 into 1, that is clockwise. Then this one 63.28, that is anti-clockwise. Therefore VD equals minus 1.75 kilonewton. We have assumed it in upward direction, but that is negative, that means that is downward. Then summation of MC equals 0, considering the LHS here by closing this portion, that is VB into 6, that one is clockwise. 20 into 7, that is anti-clockwise. Then due to UDL, that is 20 into 6 into 3, that one is, which is also in anti-clockwise direction. Then by using this we can calculate VB equals 72.78 kilonewton. Then by applying another equilibrium equation, summation of V equals 0, here we will get Vc equals 128.97 kilonewton. By using this we are able to draw the shear force diagram. Here by observing this is downward. As per our sign convention, left upward is positive, left downward is negative, that is minus 20, and the shear force remains same from this point to this point because of the support reaction VB, that is minus 20 plus 72.78, that is 52.78 kilonewton. Here that becomes positive. Then due to UDL, 52.78 minus 20 into 6, that is 52.78 minus 120, that is 67.22. That is variation is straight line. This one is positive, this one is negative. Then because of the support reaction at C, that is 128.97 minus 67.22 plus 128.97, the shear force becomes 61.74 kilonewton. Then because of this point load, minus 1.60, that becomes minus 1.75, minus 1.75 from this point to this point. And then again at D, because of the support reaction, that one is acting in downward direction, hence this becomes 0. Here this is the variation of the shear force from A to D. We will continue in the next video.